Hello, my name is Daniel Pasnani, and my team members, Kiera Maple, Neil Zhang, Andrea Nava. This is the final report for the diving project presented by Group 11. Throughout the various phases of this project, using the provided data, we calculated the initial conditions, center of mass, moment of inertia, and angular velocity throughout the dive. Additionally, we determined the number of flips achievable for various configurations and created simulations to visualize the perfect dive. Diving, at its core, is a fundamental dynamical process. The sole external force acting on a diver is gravity, resulting in constant and unchanged acceleration. However, the problem becomes increasingly complex when the diver is modeled as a rigid body with a varying moment of inertia tensor. Since a human diver cannot exert external force on themselves mid-air, they are limited to altering their angular velocities and accelerations by adjusting their body position. The objective of this project is to analyze and calculate the translation and rotational dynamics of a diver, gradually increasing the complexity of the system. For this, we have used the human model, which we'll see in the upcoming slide. This model formalizes the representation of the human body using simplified geometric shapes such as cylinders, spheres, and rectangles. The torso center serves as the origin of this model and accommodates three configurations: open, pike, and dance.
As part of the introduction, we need to show the human model configurations. Knowing the human model configurations will help us be able to solve for center of mass and moment of inertia matrices, which will be used later on to simulate the dive as the diver goes throughout the air. For the human model configurations, the biggest image shows it in the standing position, which is helpful in seeing the axes that the body is about and how big each piece is relative to each other. The origin is also placed in the center of the torso, which is useful for calculating the center of mass, explained later on. We also have open, pike, and dance configurations. Open is where the arms are raised above the head, so they have changed in the Y direction. Pike is where there are changes about the X direction because the diver goes into a ball. And then for dance, the arms and legs are rotated for 30 degrees in the negative X direction. Once we know the configuration of the human model as it dives, we can calculate center of mass. We already have the center of mass and moment of inertia matrix for the standing configuration, so we must calculate it for the open, pike, and dance. The above equations show the calculations for the x, y, and z coordinates of the center of mass. To compute, we need the center of mass of each part of the body relative to the origin, which is the center of the torso. This value is multiplied by the part's mass and added to the individual centers of mass for each. Then each is divided by total mass. Shown below are the center of masses for these three configurations using that equation. As seen, for open, it only has a center of mass in the y direction because it is standing straight upright. For pike, it starts to move its body parts around the axes, resulting in x and y center of mass, and for dance, because of the rotation of the arms and legs, there is a center of mass in the z, but not in the x direction. These center of masses can be used to calculate the moment of inertia matrices for the same configurations. The moment of inertia matrix is made up of moments of inertia and products of inertia. The moments of inertia are always positive, while the products can either be positive or negative, or are sometimes zero. This is in the instance where there is one or more axes of symmetry. For open, there are only moments of inertia because the body in each component has two axes of symmetry, but pike has a POI in the XY direction, and dance has a POI in the YZ direction because symmetry is lost as configuration was changed. Moments of inertia are calculated from the first three equations, using the integral of the sum of the other coordinates multiplied by mass. This is in order to calculate moment of inertia about the center of mass of the part. In order to relate it to the entire piece, parallel axis theorem is used, with the coordinates being the vector between the two center of masses. Once the moment of inertia matrix is calculated for each part, they are summed into the IXX, IYY, and IZZ coordinates as shown for open above. Next, for pike, the products of inertia are calculated using the next three equations. These equations give center of mass about each shape that is not symmetric about the axes or their center of mass. Next, parallel axis theorem is used to relate the centers of the body and shapes together. Lastly, Dance uses direction cosine matrices because the reference frame has changed due to rotation. So the regular moment of inertia matrix is transformed back into the inertial frame for the arms and legs, with parallel axis theorem being added to relate each inertia. The results are given in the last table for each. Lastly, for the center of the mass, initial conditions were used to find the center of mass velocity and the response of the center of mass. For phase one, this is where the primary focus was. It is known that there is only a force in the y direction, which is the gravity force. So it was integrated to find the equation for velocity, which was then again integrated to find the equation for position. At the peak height of the dive, y velocity is 0 and position is known. So time was solved for from the position equation, and this was substituted back into the velocity equation to find initial velocity in the y direction. To find Vx, dive time was doubled to where y position was 0, so then velocity was able to be solved for, as there are no forces in the x direction. The response due to these conditions was that there are changes in the y velocity because of gravity, but not in the x direction. So as configuration changes, Vx does not change in the body frame, so energy is conserved in the x direction. This can be shown in our linear momentum and angular momentum conservations, which will be explained later on as we calculate the moment of inertia matrices and show the dynamical equations in phase 3. In order to do the visualization, we had to use MATLAB visualization plots and 3D. And using that for phase 1 and 2, we modeled the center of mass in the visualization plots using a straight line in order to show the center of mass. In order to do that, we use initial conditions, creating in a loop and arrays at each time step for the trajectory of the center of mass, using rotation angles, velocity, position, and applying the rotation to the center of mass. Then we added labels and pauses for a smoother transition and to label the graphs afterwards, recording the graph as it moves through space and time. For the 3D in phase 3, we modeled the rotational dynamics of a diver based on the initial moment of inertia matrix changes and angular velocities. Then we solved the dynamics of the dive and visualized the trajectory and rotation of the diver in 3D. Then we enhanced visualization with a more refined depiction of body movements and annotations at different dive phases. In phase 1, we see the dive visualization. This is useful in showing the path and trajectory of the center of mass as the object is moving through the air. We see that it jumps off, hits a peak around 4 meters, and then goes all the way towards the bottom where it eventually stops as the diver hits the water. Next, we have phase 2. For our regular dive, we use the same simulation methods of using a line to simulate the center of mass, but we had a regular dive and a nice dive. It was a lot quicker to show the flips and dives as it goes through with the regular dive, calculating 2.5 flips without changing the angular velocity calculated in phase 1. For the nice dive, we can see a little bit slower, landing at a different because we changed the angular velocity at the start. Lastly, for phase 3, we have our 3D animations using a cuboid that changes shape as configuration is changed throughout the dive. For the initial dive, the regular dive that does not change initial conditions, we get animation as it moves slowly that it flips through the air, changing how big it is, and then it eventually lands on the stomach. So this is not a nice dive. In order to get the nice dive, we have with the dynamical equations in order to get lands on its head as if it was an actual diver moving through the air. Even though it's moving a little bit slower, we see the changing configuration the object is moving. So it comes from a standing configuration into pipe where it shrinks down in size, and then it goes back out into the open after dance configuration as it's launching into the dive. From there on, we can see how we simulated and visualized 3 different phases using MATLAB plots and simulation. For the first 2, they were simple simulation and visualizations because we did not have to analyze the complexity of the equations. However, for The dive visualizations of phase 3, we needed more complexity because we're adding transitions and we're adding a change in the configuration of the body even more for the dance configuration. Therefore, we have these cuboid shapes that can simulate the body and accurately depict where the diver is going at what time with the vertical position and time velocity.
In conclusion, this project provided a valuable opportunity to bridge theoretical knowledge with practical application. Through the process, we applied class concepts to the real-world scenarios, calculated center of masses, and varying moment of inertia, and utilized ODE solvers with MATLAB simulations. The principles of angular momentum conservation and Euler's rotation dynamics were essential in analyzing the diver as a moving rigid body. By modifying initial conditions, we were able to explore and achieve optimal results, demonstrating the intricate interplay of translation and rotational dynamics in diving motion. Thank you.